Greetings and salutations, magical chemists. Let's talk today about the glories of electromagnetic radiation, also known as EMR. This is a form of energy that exhibits wave-particle duality, which means sometimes it behaves like a wave, but in some ways it behaves like a stream of particles. Electromagnetic radiation particles are called photons. Light, visible light, is, of course, one type of electromagnetic radiation, but there are lots of others, and all of them are made up of photons, which are particles of electromagnetic radiation. But the crazy part is that they have zero mass. All right, there are two equations that we will use and that are given, shocking, they are given to you on the formula chart. And these equations look at the relationships between the energy, wavelength, and frequency of any electromagnetic wave. So the first one shows that the product of the wavelength, which is represented by lambda, and the frequency of that radiation, which is represented by the Greek letter mu, when you multiply them together, you will always get a constant, at least in a vacuum. The speed of light, of course. You may have seen the speed of light before as 3 times 10 to the 8th meters per second. Well, in chemistry, we're going to get a little more specific. It is more officially, more sig figs, why not, 2.998 times 10 to the 8th meters per second. Notice the way that they like to write this, of course. So meters per second, this just means m over s. I don't know why the formula chart loves to be fancy. They only like to use -1, but that's the same thing as dividing by it. Now, they only give one equation that is used to calculate the energy. So to find the energy, and this is the energy of one photon, the energy of this photon is going to be equal to another constant. This one is called Planck's constant, and it's not Planck like a board, it's Planck after the guy, so it's spelled a little bit differently. But Planck's constant is, of course, constant, and it's a teensy-weensy number, 6.626 times 10 to the -34th joule seconds. When you multiply Planck's constant times the frequency of any electromagnetic wave, boom, you now know the energy of that particular photon. So those are two equations, and we will do delicious mathy math with them. It will be awesome. But before leaping into our delicious mathy math, let's talk a little bit more and take a look at the entire electromagnetic spectrum. So the electromagnetic spectrum goes all the way from radio waves, the lowest energy and longest waves. These are literally like mountaintop to mountaintop for one wavelength, for a radio wave. And then all the way up to gamma rays, which is crazy, crazy short wavelength and a super high energy, which is why they are very bad for you. If you're ever not sure where the high energy and the low energy end of the spectrum is, just think of things people are afraid of. People are totally afraid of nuclear bombs and things like that, as they should be. They are not afraid to stand in front of the radio, as they should not be. So, radio waves, super low energy. And of course, lower energy means the longer wavelength, because energy and wavelength has an inverse relationship. If you have a long wavelength, that means your frequency, how frequently you pass by, well, it's not going to happen very often because your wavelengths are huge. So, the way to remember this, the fact that on the radio end of the spectrum you have a long wavelength, but you have a low frequency and low energy, is that you can remember this is the L-cubed end of the spectrum. Which means on the gamma ray end of the spectrum, the really high energy spectrum, you'll notice the wavelengths really small, really close together. So they have very short wavelengths. But that means they're coming by very, very, very frequently because they're so short. So if you have a higher energy, you're also going to have a higher frequency. So this is the shh end of the spectrum, which just stands for short, high, high. Now, almost exactly in the middle-ish is a particular part of the spectrum that we care greatly about because it is beautiful. And, it's all the stuff we can see. We like looking at things. This is, of course, the visible light spectrum. You do need to know the order, according from lowest energy to highest energy, of all the different colors of light. Luckily, this is just the order of the rainbow, or Roy G. Biv. Red, of course, is the lowest energy light, and one of the ways you can help yourself remember that is it's right next to the infrared, or IR spectrum. Violet, the highest energy light, is right next to ultraviolet, which, of course, think about it. People are trying to protect themselves from UV radiation. Your sunglasses block UV rays. Your sunscreen blocks UV rays. Nobody's trying to protect yourself from IR radiation. IR radiation, by the way, infrared, we can't see it. It's below the visible spectrum, but you can feel it. That's what heat feels like. Well, or that's what feels like heat. That would probably be more grammatically correct. Okay, so now you have a better sense of what electromagnetic radiation is. Let's go ahead and do some mathy math with it. I know you've been waiting. Okay, first problem. These are honestly very similar to physics problems in that you're always going to have a given and you're always going to have an unknown, and it's really helpful if you identify what your given is and what your unknown is to correctly pinpoint the equation needed. So here you are asked to find the energy of a photon. Well, energy, of course, is the variable E, so this is our unknown. But it says we have a wavelength of 8.27 times 10 to the negative 7th meters. Well, wavelength, you may not recall, but you're going to definitely recall with practice, this is what we represent with the Greek letter lambda. So we have a known lambda and an unknown energy. Well, let's look back at our equations. Okay, well, our unknown was energy, so we definitely have an equation to solve for energy. But our given was lambda. There's no equation that has both energy and lambda. But wait, we can still do this because, notice, the equation for energy requires you to know frequency. And you can use this lovely equation over here to solve for frequency. And then, once you have frequency, plug into the energy equation. Or if you're feeling fancy, you could even combine the equations. Let's try it just for fun. So I have my two equations, but I need to solve for frequency in terms of wavelength. So let's rearrange our speed of light equation. Well, to get frequency by itself, I just need to go ahead and divide the speed of light by lambda. So I can take this and substitute it in for frequency in my energy equation. So now we basically have a third equation we can use that says energy is equal to Planck's constant times the speed of light divided by wavelength. They're not going to give you that equation, but hopefully you can recognize it's just a really simple thing to derive and thus use. Because now we just need to plug in all those tasty numbers we know. You may be thinking, wait a second, there are 3 variables and I only have one given. But H and C are both constants, so they are constantly the same, which means you just got to go look them up if you don't remember what they are. Make sure to write them down with their units, so I can show you a cool trick. Okay, first I can plug in my constants, and then I just go ahead and take my given for the wavelength. All right, this may not look at it, because for chemistry, this is not our normal form of dimensional analysis, but if you're plugging in the units, you can do dimensional analysis to make sure you know exactly what unit you're going to get. And it makes sure that you're putting your given with the correct unit as well. Because it turns out, to use this equation, you have to have the units of your wavelength in meters. And here's why. It is because when your wavelength is in meters, that meters will cancel out the meters from the meters per second on the speed of light. And then, if you look at the units for your Planck's constant, joules times seconds, hey, look at that. You're multiplying by seconds. You're dividing by seconds. Those seconds are dead to us. So that shows that our answer, once we plug in numbers, yay calculators, is just going to be answered in joules, because it is the only unit we did not cancel out. And so, keeping our 3 sig figs, we discover that the energy of a single photon with this particular wavelength will have, well, okay, that's a kind of tiny number, but 2.40, yay, 3 sig figs, times 10 to the negative 19th joules. Now, that is a really tiny number. So that's one of the reasons why we will often convert, instead of just asking the energy of one photon, we ask about the energy of a mole of photons. Yum. So let's go ahead and look at how that could be applied on a problem on the next page. You know what? Before we go to the next page, I think the next practice problem will make more sense if we actually do convert this energy, because this was the energy of a single photon. Let's go ahead and add a part B to this problem, just for fun. So we're going to go ahead and take the energy that we just found in joules and convert it into energy in kilojoules per mole. which basically means instead of the energy joules of a single photon, now we're going to find the energy in a mole of photons. Luckily, this is just a quick bit of dimensional analysis. Real dimensional analysis, the chemistry kind. We're going to start with the energy we already have. And up until this point, we've just been acknowledging, like just saying, oh, that's the joules in one photon. Let's make that for reals. This is officially the joules per one photon. So we're adding this to the bottom because it's going to make the rest of our dimensional analysis easier. So it's the same answer from before. Now notice we were in joules, but we want to go to kilojoules. So let's do that one first because that's the easy fix. Notice joules is on top, so that means the joules is going to go on the bottom of my conversion fraction. And then kilojoules will be on top. Hopefully you remember in every 1 kilojoule there are 1,000 joules. So now if I look at my units, joules are gone. I have the kilojoules that I wanted. Awesome. But now I need to get the per moles. So instead of being per photon, it needs to be per mole. So this is where things get a little sneaky. Because photons are on the bottom in our given number, photons needs to go on the top of our conversion fraction, which means my mole of photons will be on the bottom. Now, filling this in is fun, but it's just like any other conversion where you're converting between the moles and any unit that's not grams. Because in every 1 mole, well, they're defined to be at Avogadro's number of things. So there's still going to be 6.022 times 10 to the 23rd photons in a mole of photons. Just like there would be 6.022 times 10 to the 23rd puppies in a mole of puppies. That would be a lot of puppies. So now let's check our dimensional analysis. Now the photons on the bottom are canceled by the photons on the top. So hey, look at that. My only units left are kilojoules on the top and moles on the bottom, which is what I wanted, which means my math is right. So now I just need to plug into the calculator. So with 3 sig figs, I get 145 kilojoules per mole of photons. So you notice 145, that's a way nicer number than that whole 2.4 times 10 to the negative 19th, which is one of the many reasons we like to use the unit of kilojoules per mole of photons instead of just joules, even though both of them are a measure of energy. Okay, now that we've got that and we remember that dimensional analysis fun and excitement, we're ready for the second practice problem on the next page. This one's a little sneakier, but it's not too bad, because this time you have a molecule of hydrogen, and it's absorbing a photon, a single photon of electromagnetic radiation, and that photon has a wavelength of 300 nanometers. And it turns out, flashback to thermochemistry, the bond energy of hydrogen is 432 kilojoules per mole. So there are 2 different givens here. The first thing they would like us to do is to go ahead and calculate the frequency of the photons in hertz. So remember, if we're looking at the photons, that means we're talking about the ones that have this particular wavelength. So now we just need to plug in and solve for wavelength. I think you can try that. So go ahead, given the wavelength, find the frequency. When you're ready to check your answer, unpause the video. First, recognizing that if we have frequency and wavelength, we're using the speed of light equation, rearranged it to solve for frequency. But now you have to watch out for your units. This is why you always want to write your units on your constants. So when you're writing in the speed of light, you of course are noticing, because you wrote your units as in meters per second. So if you start to do something like this, writing 300 nanometers, well, hopefully you would realize, gasp, if I have meters on top and nanometers on the bottom, it doesn't cancel, which means, can't use nanometers. So before you can plug into this equation, in fact, all of these equations, wavelength always has to be in meters, because otherwise it won't cancel. But now that we've converted to meters, hey, look at that. We get 9.99 times 10 to the 14th, and our unit, all that's left, is 1/seconds. But wait a second. They told us we had to answer in hertz. Well, it hurts me if you forgot that 1/second is a hertz. So it's totally okay. You can either leave it as 1/seconds or replace it with hertz, which is exactly the same thing. Of course, you could also, if you want to be all fancy pants like the AP, just do second minus 1. It is the same thing. Okay, So we got part A, now we need part B. Calculate the number of joules required. So joules, that's energy, required to break the bond in a single molecule of hydrogen. You may be thinking, but wait, I thought they gave me that. They gave me the bond energy. Oh, they did, but they gave it to you in kilojoules per mole. Now, this isn't moles of photons because we're talking about hydrogen. This is moles of hydrogen bonds being broken. So what they're saying in part B is, well, you better work backwards and take your kilojoules per mole and convert it back to just joules, basically undoing what we did in the made-up part B on the previous page. So this time I'm starting in kilojoules per mole, and I'm going to work backwards. I'm going to do what I always do, and I'm going to get rid of kilojoules first because it's just so easy to get rid of. Well, I'll put kilojoules on the bottom because I want to get rid of it and cancel it out, which means joules, what I'm trying to find, goes on the top. And of course, in 1 kilojoule, there are 1,000 joules. I don't know why that sounds so exciting. It just does. So once we have that, now we've been able to eliminate the kilojoules. So now we need to eliminate the mole. Oh no one should ever eliminate the mole. But in this case, we have to. So this time, notice, of course, the mole is on the bottom. So if I want to cancel it out, I need to put the mole on the top in my last conversion fraction. Well, what goes on the bottom, you might ask? Remember, we're looking for a single molecule. So we're converting from moles to molecules. And I'm sure you know, in 1 mole, there are, of course, Avogadro's number of molecules. So then we just, well, first let's make sure our dimensional analysis worked by killing things, by removing units. This time, because mole was on the bottom and mole was on the top, it is dead to us. So all that we have left is joules per molecule, which exactly what they're asking us for. So we can just plug into our calculator, confident we will get the right delicious answer. So with our sig figs, we get our 7.17 times 10 to the negative 19th joules. Notice, we don't usually say per molecule. You could do joules/molecule, but it's usually just implied. All right, last but not least, does the photon, remember we were originally talking about a photon in part 1, does it have enough energy to break this bond? Well, okay, I know the energy that it takes to break the single bond. What I need to know is the energy of this photon. So that means I have one more calculation to go. I need to calculate the energy of my photon. Luckily, I already know the frequency of the photon. We did that in part A, so I can just plug into E equals h nu. Notice that when I plugged in, using my units of course, I replaced the hertz with that 1/2 just to show that, hey look, that second cancels and that second cancels, leaving me in units of joules for my final answer. So that means 1 photon of the electromagnetic radiation has an energy of 6.63 times 10 to the negative 19th joules. But we haven't answered the question yet. We wanted to know is, does this photon have enough energy to break the bond? Well, if you're going to figure out if it has enough energy, you got to compare energy of the photon versus the energy it takes to break the bond. Uh-oh. The energy of our photon is lower than the bond energy, which means, too bad, so sad, it does not have enough energy. My little arrow thing is not a sufficient explanation if this is a free response. Let's add some numbers and words. It'll be great. Okay, so as far as explaining, there are 2 parts. I have to compare the 2. It's not enough to just have the numbers on your paper somewhere. You have to compare them. And then you've also got to say, so what does that mean? If you want to get credit on a free response, you need this part and you need this part to get you those points. All right, we have reached the end of this electrifying, if you will, video. So I will see you in our next video. I believe it's all about the joys of spectroscopy. Can't wait to see you there.